So in the last video, we introduced the idea of quick find, and that did a really nice job finding the set that any particular node was associated, mapped from like the node, the value itself, to what set ID it belonged to. And in QuickUnion, we're going to try to speed up the fact that quick find did not do a good job when it came to actually unioning those sets. So in order to do QuickUnion, we're going to have to change how we represent the data pretty significantly. So the key idea behind quick find was tracking each element's ID. We had that map from element to what ID did it belong to, which set ID did it belong to. In QuickUnion, we're going to kind of change this up a bit. We're going to kind of represent these sets as their own tree structure. So each element is going to keep track of its parent, and only the root of each of these individual trees will keep track of the actual ID for the set. So for example, Joyce, Sam, Ken, and Alex in the abstract view of this disjoint set belong in the same set. So we're going to kind of represent them as a little tree like this, where they kind of all belong in that same little family. Now, instead of just calling them regular trees, we generally call these uptrees because, and I know it's not the most clever name in the world, but the reason we change this is they have a slightly different purpose. Each node keeps track of its parent. So Alex might keep track of Ken, who might keep track of Joyce. And I said that the root of each of these trees is going to keep track of the ID for the set. So Joyce at the top keeps track that everything below her and everything below are at set ID 2 or something. You can see that each one of these kind of independent subsets has their own little uptree where the root node keeps track of that set ID. So these little tree structures are going to be what's going to help us answer these questions of, are these two values in the same set and how do we union? I do want to highlight something that can be a little bit confusing, is that these trees here are different than the edges of our minimum spanning tree. So saying that Ken is a child of Joyce in this example is not saying that there's necessarily a direct edge between Ken and Joyce in our original graph. This is a different data structure to keep track of which vertices or which any element belong in the same subset. So this is a different tree. But we're going to use it to help us find those minimum spanning trees when we get back to Kruskal's. So how do these tree structures help? I think if we talk about the actual implementations of these operations, it'll make a little bit more sense. So in order to find, suppose I want to find what set does Ken belong to? Well, we need some way to jump to the Ken node at first. So go to the Ken node and then travel up the tree, because it's an up tree, until you get to the root of that tree. And then you can return the ID. So you start at Ken, go up to Joyce, and you can return the ID for this one too. Now, this will now enable us to be able to find our two values in the same set. So for example, if you say find Santino, you start at Santino and go up. You find the root has an ID 1, so you return that. Similarly, Ken, we said ID 2, and we know because those IDs are different, they're in different sets. So they're not part of the same subset. Now, one important note about this implementation is that we're going to need some way of magically jumping to one of these nodes. We need to say, if I want to find Ken, then I need a way to know that Ken is right here in this particular subtree. The way we're going to do this is we're just going to store an extra map. We're going to store a map that lets us know exactly which node in the subtree belongs to each individual value. I'm not going to show you this map in the rest of the slides because it's going to get kind of noisy, but do know that in order for QuickUnion to work, we need this extra data structure behind the scenes to help us quickly jump one of these nodes. So now that we've talked about find, going up the tree till we find the root, let's talk about how we're going to do union. So the key idea of and why we're using these uptrees is that you could just rearrange the pointers. If you want to combine these two separate subsets, we just need to rearrange the pointer somehow and choose one of them to become the new root. So if we think about these two implementations, suppose I'm trying to union Ken and Santino's set, then I have one here that finds the root for Santino and then sets Ken to point to that. Or I have this other implementation that finds the root for Ken, finds the root for Santino, and then makes Ken's root point to this. Think about this for a second. Which one of these implementations do we think we would like more? So think about how we would use this. Which one do we prefer? Take 1 second and try this out. I don't have a poll question. So if you draw out what these look like, you'll find different answers. Each one of these kind of pseudocode algorithms describes something else. So in this first one, it says, okay, start with Santino and find Santino's root, which is Eileen. And then we say set Ken to point to that root. So we take Ken here, and I guess all of Ken's children, and we move them over to this tree. And this would be our final result. So we've successfully unioned Ken into Santino's set. But unfortunately, this kind of breaks the semantics of what we wanted that disjoint set ADT to manage. Remember, when we were unioning two sets, we wanted to combine all of the elements in those sets. So we wanted Joyce and Sam to also be kind of in that Eileen Santino set as well. And that's what this second implementation finds the root for Ken, which is Joyce, finds the root for Santino, which is Eileen, and then sets one of them to point to the other. And so now we have one kind of mega tree to represent that they all belong in the same set. You can check this out. You can run find on Sam. That would be Eileen 1. You could also run find on Santino. That's still Eileen 1. And so now we know they're part of the same. These uptrees store all of the values that belong in each of the individual subsets. And we can join them together. We can combine them by just setting one of them to be a child of another. So this kind of quick union structure is kind of exactly what we want in order to be able to union quickly, that we just have to change these pointers. So one thing I want to quickly mention, though, is that there's another maybe tempting implementation where instead of finding the roots of both, you find the root for one, so find the root for Ken, and then set Ken's root, which was originally Joyce, to point to Santino. This technically works, right? Because now you make all of Ken's family kind of move into the Eileen Santino tree. But we actually still prefer this one on the left. Why? This one on the right is going to tend to have a longer tree because we're taking the root of Ken's tree, Joyce, and then sticking it underneath Santino, who's not necessarily the top of his tree's family. He might be a leaf node, right? And so we are going to be extending the heights of these trees if we are always sticking at the bottom of a tree. So the key idea here is that in order to make the future runtimes for find fast, we want to keep these trees as short as possible, because to find a set for a particular value, you have to start at it and go all the way up. So we want these trees to be as short as possible. So if we look at these runtimes now, if we're thinking about this quick union, the find set operation, now in the worst case, you have to kind of start at the leaf node and go all the way up. And maybe we have this worst case linkless tree. We'll have O of n operations there. Now, union can be fast, assuming we ignore the calls to actually finding something. Remember, for union, we have to find A, find B, and then set those pointers. And we just said that find takes O of n time. So union will still be O of n, except if we assume we're in the case where we're only unioning roots. So if I know that these two things are roots, then it's just constant time. Now you might be wondering, hey, is that even a valid assumption to make? And the answer is yes, totally. For Kruskal's algorithm, we always only union roots. Notice what we did in our algorithm here. We found the MST for U, we found the MST for V, and then if they didn't agree, then we union them. But we always called union passing in roots that we already called to find. So union can be fast, assuming you don't also have to do finds. So we actually might want to analyze those as separate cases. But yes, in the worst case, when you're just unioning arbitrary elements, you're going to have to do a find operation, potentially going all the way up the tree. So let's try to go ahead, and you might be wondering, well, how do you go and make this kind of worst case? So assume I have these A, B, C, D kind of elements. They're all start in their own sets. How can I build up this worst case element, this worst case structure? And the idea might be if you keep unioning one next to the other, always joining kind of the first one onto the second. So maybe you do something like union A and B, which would then make A a child of B, then union B and C, and make B a child of C, and then union C and D and make C a child of D. Then when you try to do this find A, you have to go all the way up the tree. It would be nice if we can try to guarantee that this tree was balanced. So what it would be kind of nice would be if we were trying to union C and D, and if we had C being ABC and D on its own, it would be nice if we can kind of be a little bit cleverer, a little bit more careful about how we organize these trees. Instead of making C the child of D, what if we made D the child of C? Just swapped the way that we kind of made it one the child of the other. So the key idea for what we're going to improve for the next one is, what if we always make the larger tree kind of the overall root? So if we're going to get this degenerate tree, if we always make the large tree a child of a small tree. But the idea is, if we make the small tree a child of the large tree, we hopefully shouldn't increase height. And that is kind of where we're going to pick up in the next video, where we talk about weighted QuickUnion, trying to be a bit smarter about which one we make the child of which. But it's going to be a very similar idea.